The last couple classes talking about the inverse function theorem, which was a beast to prove last class, but we did it. That's probably the hardest thing we'll have to prove this semester. So now I want to move on to the case where the number of inputs to our function is different from the number of outputs, and see what we can do here. So the topic of this is the implicit function theorem. So let me give an example first of all. So let us suppose that you have a factory that makes, let's say, microchips. I think there's a microchip shortage still. So we need you to make more of these for us. And of course, what you want is to maximize your profit. Now, your profit depends on a lot of different things, many of which are outside of your control, some of which are inside of your control. Okay, so let's call these different variables. Maybe U is the number of items produced. You have control over that. You can ramp up production or ramp down production. Now, there's a lot of other things you don't really have much control over. They'll vary over time, but you don't specifically get to decide what those are. For example, maybe the price people are willing to pay for these things. There's cost of materials. There might be demand, and maybe others. Okay, so this is a function of a whole bunch of different inputs, but it's a real valued function. It spits out only one output, scalar valued. Now, what do we want to do? You want to maximize profit, of course. So we have this function. We only have control over this variable. We can ramp up production or ramp it down. The others are kind of fixed by the more general market. So we want to try to maximize profit over all U. We want to find the U that maximizes profit. So we know that maximization problem, we should take the derivative and set it equal to 0, and that will help us find our maximum. So to maximize this, we want to find some mu such that df by du is equal to 0. Okay, let me call this function g. So g is going to be defined as df by du, and we want to set g equal to 0. Now, g is a function. This would be an example of not a square transformation. It's a function of a whole bunch of variables, but only real valued, one output. And now our question is, given that g is equal to 0, or that we would like g to be equal to 0, can I solve for u in terms of all of these other variables? So given that I know all of these things, which again may change over time, but I can figure out what they are, can I solve for u? So this is our question. Can we solve for u in terms of these other variables? And this is the question that the implicit function theorem seeks to answer. Because we have a non-square transformation, different number of inputs to outputs. Can I solve for some of the variables in terms of all of the other variables? So this is what we're going to try to do today. Today I'm going to spend a lot of time again just motivating it, building intuition, trying to figure out what kind of theorem we're likely to be able to prove. And then I guess we won't get to the proof of the theorem until after the midterm. The good news is the proof shouldn't be quite as hard as the inverse function theorem. We did most of the work there. So let's start with some simple settings. There's two basic simple settings that we can think about to gain intuition. One is low dimension. let's take the dimensions as low as possible. Low as possible would mean that, well, one variable that I'm trying to solve for in terms of maybe just one other variable. So here I would be have g going from R2 to R. That's the lowest dimensional setting. And then we can start to draw pictures and think about things, gain intuition. And then the other obvious simple case is the linear case, where it's kind of easy to see when we can solve things and when we can't. Okay, so let's start low dimensional. Okay, so let's suppose that f takes R2 and maps it into R. And we're interested in solving f equals 0. All right, so let me attempt to draw this. And let me apologize in advance for my artistic skills. So I have x and y as my two variables, and then I'm going to plot f on the z-axis. Okay, and what am I going to have? I have some kind of profile. Okay, and maybe I can dot this a little bit. This is back here. And now what are we trying to do? We're trying to find out where f is equal to 0. Okay, so f equals 0 is where we hit the xy plane. There's not going to be a unique solution, right? In this picture, you can see there's not going to be a unique solution. There's going to be a whole curve of solutions. Okay, so we're interested in this curve, the 0 level set of f. And we want to try to characterize this curve somehow. All right, it should be no surprise, given what we've done over the last week, that we're only going to be able to do things kind of locally, right? So we're going to pick a reference point and just try to figure out what happens nearby. Okay, that again should be no surprise. That's all we could do with square transformations, so this is probably not going to get better here. Okay, so we pick some reference point. Since we're only going to do things locally, I'm certainly not going to pick something in the middle as my reference point, because in a little neighborhood of the origin here, for example, nothing interesting that I care about is going to happen. So we need to start with a reference point that's actually on our curve. So we need to start with at least a single solution of f equals 0. There's infinitely many. We need one. So we try to find something that's easy to find. So I'll call this point x naught, y naught. And we want to characterize the points on this curve, and we'll probably do it locally close to x naught, y naught. All right, so let's move from our 3D graph to our 2D graph. Okay, so I'm going to just take the points on that curve and plot them. And again, apologize that this may not look very much like the 0 level set of that, but you get the idea. Okay, and again, we have a point right here, x naught, y naught, where we're going to try to locally do things. Now, what do we want to do? We said we want to solve for one variable in terms of the other variable. So my question is, can I find a function g, okay, such that I can write y equals g of x, at least locally? Okay, I think it should be clear from the picture, I hope, that at least locally is important. I'm not going to express this whole entire curve as a graph. It's not a function. But locally, maybe we can do it, right? If we just zoom in on a little window here, that looks like a graph. So the question is, can I do it, and when can I do it? So can I do this for any choice of x naught, y naught? No, right? There's going to be some cases where there's a problem. So this point looks okay. If I picked maybe this point right here where I have a vertical slope, that would be not okay. Okay, so we can do this as long as the curve doesn't have a vertical slope. Okay, and in that case, what happens? We're trying to solve f of x, y equals 0. We claim that this is true as long as y is equal to g of x. Okay, so in that case, we should have that f of x and g of x is equal to 0. Okay, and since we're doing this locally near our reference point, we expect that y naught is going to be equal to g of x naught. Okay, so let's try to figure out what's the difference between this point and this point. I mean, we know based on this curve that the difference is whether the slope is vertical or not. But if all I'm given is this function and I don't have really clear understanding about what its zero level set looks like, that's what I want to find, then how do we decide just from this function which points we can do and which points we cannot do? Okay, so let's find a problem point over here. We said a problem point is where the slope is vertical, okay, points in this direction. So something over here would be bad. Okay, so this point here, can't do it here. All right. This curve here is the zero level set of f. That means f is constant on this curve. As I travel along this curve, f doesn't change. Okay, so we know about constant functions. If I think about simple functions of one variable, if the function is constant, its derivative is 0. Okay, well now we're going to have that kind of effect here that the derivative is 0 along the direction that we're traveling here. Okay, so because f is constant along here, in the direction that I'm traveling, that's the tangential direction, that means the partial derivative in the tangential direction is 0. Okay, and that's where I have problem points. Okay, so we're in trouble. Okay, so since f is constant on the curve, the zero level set curve, okay, the partial derivative is going to be 0 in the tangential direction. So its partial derivative is 0 in the tangential direction. And based on this picture, we don't want that to happen when the tangential direction is the y direction, is lined up with y. So this is where we run into problem. So we have a problem when the tangential direction to the curve is the y direction. Okay, what's another way of saying that? It means that if I travel in the y direction, my function is constant locally. So another way of saying that is if df by dy is 0, we're in trouble. Then we can't solve for y. Okay, so what's the distinction here? We have our two variables. Y is the one that we were hoping to solve for. If the partial of f in the direction that we're hoping to solve with respect to the variable we're hoping to solve for is 0, we're in trouble. All right, let's keep that in the back of our mind. We want to try to generalize this to higher dimensional objects. Okay, so we're going to need an assumption that says if I want to do implicit function theorem, if I want to construct this function g locally, it can't be the case that the partial of f with respect to the variable I'm solving for is 0. And we've got to bring that up to a higher dimension somehow. Okay, so just to take an easy example. X squared over 9 plus y squared over 16, fill out that 9 a little bit, minus 1. Okay, we're interested in solutions of f of xy equals 0. So what does that curve look like? Yeah, an ellipse, yeah. Okay, so what we're interested in are things that lie on this curve. Here's 3, here's 4. Okay, and if we want to solve for y in terms of x, this is just a quadratic equation. We're going to get solutions of this form. Okay, so our g of x that we're seeking is going to look something like this. And then I guess we have a couple questions. What values of x naught can I do this for? What size neighborhood is this valid in? And then I guess which sign do I have to pick? Because there's a plus or a minus. So first question, I guess, what values of x naught is this valid for? Yeah. Between negative 3 and 3, yeah. Including the endpoints or not including the endpoints? You say including? Okay. If you include the endpoints, you have a vertical slope. That's right. So including the endpoints is probably not a good idea because at the endpoints, I've got this vertical slope that I don't want. Okay? So we should be able to do this. Okay, for x naught in this interval. Okay, again, otherwise we have this vertical slope. And which sign do we pick? The plus sign or the minus sign? All right, so remember when we said when we're doing this locally, you want to hazard a guess?
It depends on the starting point.
It depends on the starting point, that's right. So we said we're doing this locally. That means, all right, I have a function of two variables. I need a starting point for both variables, right? And the starting point is not going to be the origin because that's not going to take me anywhere close to this curve. So I need not just an x naught, I also need a y naught. Okay, and the sign of y naught is going to tell me which sign I take. Okay, so in this case, g of xy is going to be the sign of y naught times 4 root 1 minus x squared over 9. Okay, now this is not valid globally. I mean, obviously, if I try to take x out to here, it's not valid. What size neighborhood of x naught would this be valid on? If I want to go from x naught minus delta to x naught plus delta and have this be legit, how big can I take delta? It's 3 minus x naught, or 3 minus the absolute value of x naught, exactly, right? So I can keep going until I run into one of these edges, right? So 3 minus x naught, or if I'm over here, 3 minus the absolute value of x naught is going to tell me how far I can go. So this is valid for x belonging to, let's say, x naught minus delta to x naught plus delta, and delta is going to be equal to 3 minus the length of x naught, the absolute value of x naught. And that's what's going to keep me from running into this problem point. Okay, and in that case, we will indeed have that for any x in this interval, we define g this way, and we will indeed have, you can easily plug it in and check, that f of x and g of x is going to be equal to 0. So we get this local family of solutions. Okay, so these are the kinds of pieces of information that we expect to need here. We need this starting point to be able to do things locally, because we know that we can't globally come up with such a function g. So we need a starting point. We know that this is only going to be valid on some neighborhood of our starting point. It's not going to be valid forever. But then we should be able to come up with this function g. When I say come up with, I mean such a function exists. But we know that in life, not everything is quadratic. Those things get more complicated in a big hurry, right? So we're probably never going to write down a simple formula like this. We also know that if we have things that are well behaved, differentiable, functions can be well approximated by their linearization, and we've done a lot of that. So it's reasonable to wonder if we can also get at some good information about the derivative of g. Right? Since we're probably never going to write down a formula like this in real life, the best we can maybe hope for is, what is g doing at our reference point? Well, g of x naught is y naught. Okay? And then what is the derivative of g at this reference point? So can we compute g prime? Okay, of course, in this case, we can explicitly compute g prime, which is nice. It gives us a way of testing our hypotheses or our observations. But let's think about this in general. What are we trying to do? We want this. We want f of x and g of x to be equal to 0. And maybe this is all I know. You know, I don't have any easy way of solving for g. I just know this. Can I extract information about g prime out of this equation?
Yeah. Maybe do like chain rule?
Okay, we could do some chain rule. Yeah, we could do some implicit differentiation, and maybe a g prime will pop out here. So right now I've got this written really just as a function of x only. The curve that I want to, I'll put this all in terms of x. Let's take a derivative with respect to x and see what happens. All right, so let's differentiate this. Okay, and what does my chain rule say? Well, I need to take a partial of f with respect to x plus a partial of f with respect to y times the derivative of this inner function. And the derivative of 0 is 0. Okay, so this suggests that maybe I can solve for g prime as minus df by dx divided by df by dy. Once again, we see this important condition coming up, that this partial derivative with respect to y better not be 0. That would give us a problem. But as long as it's non-zero, which we're assuming it's non-zero, this is fine. This is an object that I can write down no problem. Even if f is extremely complicated, derivatives are easy, right? We can compute these partial derivatives very easily. Probably we're only interested in them at the point x naught, y naught. In general, I would have to put in x, g of x here, and I don't know g of x. But if we're linearizing, all I care about is x naught, y naught. Okay, so we'd also have g prime of x naught is going to be partial of this, evaluated at x naught, y naught, divided by the partial of this at x naught, y naught. And that's something that we should be able to work out very easily, even if f is very complicated. Okay, we can certainly do this for our example. So in our example, this formula suggests that g prime of x is equal to minus df by dx to x over 9 divided by df by dy is y over 8 Okay, so what is this? This is minus 16/9 x over y. Now y is a particular value, it's g of x. I should probably have an equal sign here. Okay, in this specific example, we had a formula for g. Okay, so this was minus 16 over 9 times x over the sine of y naught times 4 root 1 minus x squared over 9. Okay, we have a concrete formula, and then you could go ahead and check that actually that's exactly what you get if you just differentiate this directly. Okay, so this formula works. It's nice to do sanity checks once in a while and make sure things actually work in practice. So this matches, okay, our explicit formula for g. Yeah?
Can we find g from this formula?
Can we find g from this formula here? I guess you have to solve a differential equation if you want to do that. You mean from this right-hand side here? Yeah, I mean, you'd have to integrate it. Yeah. Now, of course, in general, again, this is a simple function. In general, integrals are hard, right? Taking derivatives is easy explicitly. Integrals, a lot of the time, you can't do it. So yeah, I guess in principle, you integrate this, you get g. Now, I guess we can do this for all x and y. We can get this formula not just locally. So yeah, in principle, you could get g. You could do maybe quadrature to try to approximate g. Sure. Okay, so these observations that we've made are a theorem. Like the things that we pulled out of the pictures are legit. That we can, it's called Denny's theorem, which I'm not going to go into a lot of detail in, because Denny's theorem is the low-dimensional version, essentially, of the implicit function theorem, and we want to go to the high-dimensional version. But these are sort of the key observations that we've made, low-dimensional. Okay, and which we'll hopefully be able to bring up to higher dimensions. Okay, so we can solve for y if df by dy is non-zero. And our other key observation was that g prime is going to be equal to, we have this formula here. And again, we're going to hope that we can somehow upgrade this to a higher dimensional version, which will have to look a little bit different. I'm certainly not going to just stick some higher dimensional thing in the denominator like this. But at the end of the day, we'd like a theorem that recovers these two properties when we go to low dimensions. Yeah?
Higher dimension, it will just have to have other partial derivatives.
We'll have a lot of other partial derivatives, yeah. So we'll have to, I guess, say what is the correct way to incorporate the other partial derivatives. And that information, I think, we'll get, or at least get some intuition from considering another higher dimensional setting, the easiest possible higher dimensional setting, which is the linear case. Linear, I can go higher dimensional, and it's still very easy to see what's going on. So we want to take our observations from the linear case and try to kind of match them up to what we saw here. And hopefully we get a good hypothesis, a good set of hypotheses as to a theorem that we might be able to prove. Are we happy with the low dimensional case? Okay, so our next case is the linear case. All right, so we're going full high dimensional. Okay, so we're going to consider transformations. Okay, that take a whole bunch of variables. And now I'm going to divide them up into ones that I'm hoping to solve for and ones that I'm not hoping to solve for. Okay, so this is going to take some variables in our n plus m. Okay, and map it into Rm. Okay, so with m equations, we're going to hope to solve for m variables, right? And then n are these extra variables that they'll take the place of x in our last example. Okay, so we're hoping to solve for m variables. All right, so I'm going to take my points in Rn plus m. And again, I'm going to try to distinguish them clearly. Are they the ones I'm solving for or not? So let's write our points that are in this high dimensional space in the form x and u. Okay, so x, again, are these extra variables that they're just hanging out and I'm not going to solve for them. So we had n extra variables. And the u are the ones that I'm going to solve for. And again, they're m equations, so there should be m of these u variables. Okay, so what are we trying to do? Again, we're considering f of x and u equals 0, where these inputs are vectors now. And we want to solve for the u variables in terms of the x variables. Okay, so we want to solve for u in terms of x. Okay, so again, I'm going to try to generate some kind of function g that does this. It's going to be a vector valued function now. Okay, so our goal is, can we find a function g? Okay, so what does g do? G takes as inputs these x variables. So it's going to take as inputs these n variables. And then it's going to spit out the u variables, okay, which are in the low dimensional setting, lived on this curve, which is essentially a one-dimensional object. And now they're going to lie on this higher dimensional manifold. Okay, as such that, I mean, at least locally, we're going to have that f of x and g of x is equal to 0. All right, so the linear case. In the linear case, f of x, u, I'm going to try to write as a general system of linear equations. So m linear equations in these n plus m variables. Okay? So in general, what is this going to look like? This is going to look like, well, a11x1 all the way down to a1nxn plus, and then we also have linear dependence on all these b variables. Okay, I'll give those coefficients a different name because we're trying to keep these dependencies kind of separate. So b1u1 plus bm um. Sorry, b11 and b1m. All the way down, we said we have m equations. So I'm going to have am1x1 plus amnxn, bm1u1 plus bmmum. And we want this to be equal to the 0 vector. And we want to know, all right, in what cases can I solve for this collection of variables in terms of this collection of variables? So we're in a setting where we want to do some linear algebra. So let's try to write this in a cleaner form. If I just focus on these x variables over here, you know, this has precisely the structure over here of a matrix vector product. Right? And if I just focus on the u variables, this right part also has the structure of a matrix vector product. So I should be able to write this as the sum of two matrix vector products. One matrix that acts on x, and a second matrix that acts on u. Okay, and what are these? A is an m by n matrix, so it's not squared. And B is an m by m matrix. Okay, so what do we want to do? We want to ask, can we solve ax plus bu equals 0 for u? So what's the condition that would let me do this? B is invertible. If B is invertible, I can solve this. So if B is invertible, then the solution is U equals minus B inverse AX. Okay, and this becomes my G of X. Right, and then you plug this back in here and you check that indeed f of x and g of x gives you ax plus b times all of this, so minus b inverse ax is 0. So that gives you the family of solutions that you're looking for. Now we want to make the connection, the jump. What does this tell us about nonlinear transformations? All right, in the low-dimensional setting, and we expect the high-dimensional setting to somehow have a similar flavor to the low-dimensional setting. In the low-dimensional setting, it was a statement about partial derivative with respect to y, the variable we're solving for. So we sort of expect that this condition here, B is invertible, should somehow correspond to some kind of statement about all the derivatives, the partial derivatives with respect to u. Okay, so how does this relate to the partial derivatives with respect to all these u's? Because we suspect that's what's important. Let me write down all the partial derivatives of f, okay? I'll write down my big Jacobian matrix here. So the Jacobian of f in general, okay, is going to be, well, we've got a whole bunch of equations, right? df1 by dx1 all the way down to df1 by dxn, and then I have to take partials with respect to the u variables. And go down the list and do the same thing for all the other components of f. All right, this is a big matrix, okay? So this is an m by n plus m matrix. Okay, and again, we might ask, how does this relate back to our linear setting? This is a giant matrix. In the linear setting, what would this matrix be? So if we happened to be in the linear setting where f had this form, what would this matrix turn into? Yeah.
It would be the coefficients that you want to.
It would be all of these coefficients, the a's and then the b's. So it would be really the same matrix that's coming up in this gigantic matrix vector multiplication. So I might write this in sort of a block form as, well, the first n columns are precisely the n columns of my A matrix, and the next columns are the columns of my B matrix. Okay, so this is what's the case in the linear setting. in the general nonlinear setting, again, it's maybe quite natural to try to write this ginormous Jacobian matrix in a block form, right? There's something that changes partway down here. The first bunch of columns are all partial derivatives with respect to the x variables that we're not trying to solve for. And then we have a whole bunch of partial derivatives with respect to these u variables. So I'm going to break this Jacobian up into two pieces. I'm going to say this Jacobian, the first columns involve all the partial derivatives with respect to x. I'll call this the x Jacobian. And then I have a whole bunch more columns that involve partial derivatives with respect to u. We'll call this the u Jacobian. Okay, we know from the linear setting that if this is going to work, if we can do this, we need this matrix to be invertible. That corresponds to this part of the Jacobian being invertible matrix. All right, that part of the Jacobian is square because it's the derivative of these m functions with respect to the m variables. Okay, so we're going to hypothesize we can do this locally if this part of the Jacobian is an invertible matrix, right? The whole Jacobian is not an invertible matrix because the entire Jacobian is not a square matrix. But let's focus in on the things we're trying to actually solve for. If this guy is invertible. Let's see if this jives with our low-dimensional intuition. So in the special case of m equals 1, so we only have one variable that we're solving for, what does this statement become? Okay, so what is the Jacobian of a function of one variable?
The derivative.
It's just a partial derivative with respect to that variable. So we would be asking that this partial derivative is invertible. What does it mean for a scalar to be invertible?
Non-zero.
It's non-zero. Well, that is precisely what we said should be the case in the low-dimensional setting, that we should be able to do this if this partial derivative is not zero. Okay, so what we've got here matches what we got before. It reduces to the same thing in the low-dimensional setting, and it's a statement that reduces to what we know to be true in the linear setting. Okay, so these are some good sanity checks before we try to prove something that in the simple cases it reduces back to what we know to be true. Okay, so this is correct for the low-dimensional setting. All right, are we comfortable with that as a working hypothesis? All right, then the other thing we were concerned about is, can we come up with G prime? Now can we come up with the Jacobian of G? Because G is now a vector valued function. So I'm going to erase this board, but then I'm going to remember again that in the linear setting, this was our G. Okay, so what about the Jacobian of G? Well, in the linear case, where we had that G of x was minus B inverse AX, Okay, so we can take the Jacobian of it, and the Jacobian is just going to be this coefficient matrix here. Okay, and in this particular linear case, I could interpret these matrices A and B as the different components of my Jacobian matrix. So in this particular linear case, this is minus the U Jacobian inverse times the X Jacobian. Okay, and then again, we ask ourselves, what about the low dimensional case? Does this jive? Well, in the special case of m and n equal 1, we had that g prime was equal to minus, well, the partial of f with respect to x divided by the partial of f with respect to u. I guess another way of writing that is the inverse of this times the partial of f with respect to x. So again, this fits with what we thought should happen, right? So I'm going to make a hypothesis that if we can build a G like this, well, we think this is maybe the condition that lets us build a G like that. And then in that setting, we're going to make the hypothesis that this is the Jacobian of G. And again, that we know to be true in the low dimensional setting. We know to be true in the linear setting. So it seems like a reasonable thing to try to guess at now, to try to prove. Questions? I think we're just about ready to write down a conjecture here for our implicit function theorem. Again, it's going to be, the statement of the theorem is long and detailed and technical, and I don't want us to get lost in it. We're just trying to incorporate our basic observations here. And I don't want you to panic too much either, because while the statement is a little bit more technical than the statement of the inverse function theorem, well, first of all we're stating is the things that we've just talked about and gotten some intuition for. It's like two main things, even though there's technical things that we have to write here. And secondly, we've already done most of the work of proving this, so there'll be a little bit more we have to do, but it's not as bad, I think, as the inverse function theorem. Okay, so let's make this a conjecture. So let's try to write down the conditions we think that we need to be here. So we have a function. Okay, I'll write it as I did before. It goes from Rn plus m to Rm. I'm going to kind of at least require the things that we required for the inverse function theorem, because actually we're going to use the inverse function theorem to try to prove this later. So usual things, that this is continuously differentiable on some open set, on a set that has legitimate volume to it. So suppose that this is continuously differentiable. On an open set. Okay, and S is an open set that lives in this high dimensional space. We're doing things locally. We needed a starting point. So our open set contains this point x naught u naught, our starting point, and our starting point has to live on this manifold that we care about, the manifold where f is equal to 0. Okay, so we're going to suppose that f of x naught u naught is equal to 0. Okay, and this was our claim was the important thing that we have to include here. This U Jacobian is non-singular at our reference point. So we're going to say the U Jacobian at this reference point is non-singular. Then what do we think we can conclude? Okay, let me put a picture beside this as we're talking about what we're going to conclude. So far, what do we have? We have this set S. And we have our reference point. Now, what do we expect? We expect that we're going to do things locally. Okay, so we're going to come up with a function g of x and some range of values for x, okay, such that x, g of x lives close to here. So I'll call this set M. Now this is a high dimensional set, right? But it's going to correspond to some low dimensional set because when we plug x into g, there's going to be some range of values we're allowed to plug in here. So corresponding to this, if this is my x naught, which lives in a lower dimensional set, I'm going to have another set here. These are the set of x's I'm allowed to plug in. We're hoping to come up with a function g. G will give us some range of u's. There's u naught. This set is the image set of n. Okay, so this is n-dimensional, this is m-dimensional, and when I put them together, they're going to live inside this set M. Okay, so I'm going to write down just all these open sets in different dimensions. This is what I mean by it, just that there is some neighborhood of x naught that lives in this low dimensional set, and I can write down a function g of x. By write down, I mean it exists. Okay, that gives me these family of u's, and taken together, x g of x is this, object that lives in this higher dimensional space. Okay, so this might be the family of solutions of the form x g of x lie on this curve or higher dimensional surface that passes through our reference point. Okay, so this is the picture that I want to do. Now I'm going to write it up here really precisely. So I'm going to say there exists a neighborhood M of my reference point. Which is contained, of course, in my set S. Okay, and everywhere in this neighborhood, my U-Jacobian is non-singular. That part's not a big deal to prove. That's just a consequence of the fact that we said f is continuously differentiable, so that means this Jacobian is a continuous object. So if it's invertible at this point, then it's going to stay invertible nearby. It can't instantly go from invertible to singular. So that part's no big deal. But it means that our formula for the Jacobian is a formula we can write down. Okay, and there's this neighborhood n, this lower dimensional neighborhood n of x naught. And now on this neighborhood, we can define our function g. So g is a function of x. So everywhere in this neighborhood, we can write down g of x and have it do what we want. So on this neighborhood, there is a g. All right, g is uniquely defined. Right, we saw in our low dimensional settings that as long as we didn't allow this U-Jacobian to be singular, we could do this uniquely locally. Okay, so in which there is a unique, continuously differentiable. Okay, so g is going to inherit all the nice properties of f, which is good because it means that we can do a linearization of g. Okay, so what does g do? G takes the variables in the x space and maps them into objects in our u space. And what are the properties of this? The properties of this are that, well, it contains our reference point. So x naught gets mapped to u naught. What else? We said that, okay, all of these points, right, this defines a curve that stays inside our set M. So it's not a weird function that's doing something here and then jumping far away. It stays close by to our reference point. Okay, so x, g of x stays in this neighborhood M. Okay, it's a funny looking statement, but all it means is that we're staying close to our reference point. Okay, and f of x, g of x, here's the thing we really want, is equal to 0. And moreover, we can write down a formula for the Jacobian. The Jacobian of g is exactly what we hypothesized, minus the U-Jacobian of f inverted times the x Jacobian. Questions on this? But this is a long theorem statement. But again, I want to emphasize, it really just says the two things that we were talking about. We can build this g of x that gives us the solutions to f equals 0. Okay, so f of x and g of x equals 0, and we can write down its Jacobian. Okay, and then there's technical details that are needed to fill it out. But the technical details are really just this picture, that We're doing things locally. That's really all we're saying. We're doing things locally. Are we happy with this?
Can you repeat the thing that you said about the singularity, that we cannot go from...
Where is that here? Then there's a neighborhood on which, then there's a neighborhood on which this U-Jacobian is non-singular. So the idea is that f we said is continuously differentiable. So this Jacobian is a continuous matrix. It's all its components are continuous. So the fact that it's non-singular means the determinant of this matrix is not 0, right? The determinant is also a continuous function, right? So since this is not 0 at x naught u naught, and since the determinant is a continuous function, it can't instantaneously become 0. I can draw a picture of that. You have the matrix in your mind. What's key about the matrix is it's non-singular, and that's encoded in a scalar. That's encoded in the determinant.
If we take, let's say, the matrix with all entries 1, let's say, and then the 2 by 2 matrix.
Sure.
And then the 1 element, it's 1 minus epsilon.
Yes.
This is non-singular, right?
It's still non-singular, exactly.
But for small epsilons, let's say epsilon goes to 0, this becomes singular, right? So it doesn't sound singular.
So what's your example matrix?
1 minus epsilon.
1 minus epsilon.
1, 1, 1.
Okay, so we're picking an epsilon now. So at our reference point, this is not singular, right? So epsilon is not 0 at our reference point, right? So maybe epsilon is small. So maybe epsilon is small but positive. Okay, so non-singular. Now, I'm not saying this can't eventually become singular. I'm saying there's a neighborhood on which it's not, right? So, if I vary this by, if I take this right down to 0, vary it by an amount epsilon, there's a problem. But if I vary it by an amount epsilon over 2, it's still not a problem, okay? So that's what I mean. It can't instantly become singular, right? It may be only a tiny neighborhood on which we can work. That's possible. But it's not instantaneous. There's always a neighborhood on which we can do things. And that's because it's continuously differentiable, right? This matrix is going to be continuous in x. The determinant of this matrix is going to be continuous in x. So that means it'll never go instantly from non-0 to 0.